Let's look at this chapter 11. I'm doing this out of sequence, I know, and it's important. And let me explain a little bit behind the reason to my madness here. Nuclear chemistry is very different from everything else we're going to be talking about in the course, although it's very important because there's a lot of aspects of nuclear chemistry that are important to society and how we use it. That said, it is chemistry that's involving the nucleus. And I don't want to get too far away from our discussion of the atom before we talk about the study of the nucleus, because a lot of what we used to study the atom was based on nuclear chemistry. And I already started to introduce that to you with the idea of alpha, beta, and gamma waves, but or energy. And I never really explained to you what that was. And the reason I didn't at that time is because that is nuclear chemistry, all right? So I said to you we're going to come back to that, and that's what we're doing here. But that said, it is chemistry that's very specific and not the kind of chemistry that we do habitually in society commonly. And that is the chemistry that's involving the electrons, right, of the atom, right? What we were just talking about in terms of bonding. Right, that kind of chemistry is the one that is probably what you're more familiar with in terms of what the applications are. Nuclear chemistry, like I said, is the chemistry of the nucleus, and it has its own set of rules and its own types of equations, which is what I want to go over now. And what you're looking at here is something that we're really going to lead into, and this is the idea of nuclear fission, or the breaking down of that nucleus. And I want you to sort of appreciate right now that you're starting off, and we're seeing uranium, and you're making lighter elements, and you're releasing other stuff, okay? And this is very different kind of chemistry, like I said, than we're going to talk about for the rest of the course, but it is very intimately connected to the study of the atom. So this is why I believe it's placed best here before we talk about chemical equations that are involving the electrons and all the other aspects of societal use of chemistry in the rest of the course, all right? So let's get into this. So when we're looking at this nuclear chemistry, there's this misunderstanding, I think, in society, or a lumping together of radiation. And when someone says radiation, right away people think of essentially nuclear chemistry, and you know, people start to get nervous and freak out and that kind of stuff. But when we're talking about radiation in general, a lot of what people are thinking about in terms in their heads, this dangerous nuclear reactions, is really also including, you know, when we're talking about background radiation, radiation that comes from light. So electromagnetic radiation, which we already talked about a little bit about. So remember, when we're looking at the electromagnetic spectrum, we only see visible light. But from our other discussions, you know that the electromagnetic spectrum includes all kinds of other light that we don't see, all right? And that is also lumped into this idea of radiation that we're exposed to, all right? So, and all of that together, we say is background radiation. So three-fourths, or most of the radiation we're exposed to, is what we call background radiation. And the other part is coming more commonly, not from nuclear power plants and, you know, crazy damaging radiation from nuclear reactions that we're going to talk about, but from medical things such as X-ray machines and that kind of thing, all right? So this is your breakdown, and then there's this thing that says natural, and a lot of this natural, and I mean all of this is natural except for the synthetic, which is here, but they have special categories for some parts of natural radiation, and then lump all the other one here. And the one that I want to pop out, or I highlighted here, is radon, especially for this area, because radon is coming from the soil, which is weird because they have rocks and soil separate, but for some reason, radon is over here. So I guess because it's radon gas, and it's coming out of the rocks and so. But anyways, suffice to say, radon is over here. This is a big one in New York State, especially up here in central New York. I spent enough time in New York City to still think about this as upstate, whatever that is. But anyways, central New York, and in my house here, and all my neighbors, in fact, you get your home tested for radon, and so that they put this device in your house and they measure, they collect radon emissions for several days, and then they decide whether that needs to be mitigated. It's usually in the basement. So, well, I have a radon extractor in my basement. It vents out through my roof, vents out through my garage and up to the roof. And indeed, if I look around at my neighbors, we all have these white tubes that are sticking out of our roofs, and this is because of this radon, all right? But there's other stuff. So cosmic rays, a lot of that is gamma. Internal, our bodies are also generating this. So you yourself are an emitter of background radiation. And like I said, rocks and soil. And then here's your synthetics. So these are the things that we sort of have control over. When it comes to occupational, I probably have a lot more exposure in my younger days to this because I worked in the lab. And at that time, we would use radioisotopes in the lab. And I used to use them very commonly. Now, there's a lot of stuff that used to be used using radioisotopes. We now use light emission, so conversion and production of fluorescent light, instead to detect that energy that we're trying to label or tag or follow. We're using this energy to tag molecules, for example. So it used to be tagged with nuclear, with radioactive isotopes, which I'm going to talk about in a sec, but now not so much, to try and keep lab workers more safe, right, or increase the safety of lab work. But anyway, so this is what we're talking about. So there's this. So when you're talking about background radiation, you're talking about all of it together, all right? So I just used the term radioisotopes several times. So what is that? And I've sort of graded us into this idea, right? So we started talking about the Bohr model of the atom, and John Dalton, and how initially we didn't know about isotopes when we're talking about Dalton, and that's the thing he didn't understand, is that some elements can have different masses because they have different numbers of neutrons, right? And then we looked at isotopes, right? First, at different masses, and then I said, well, these different masses come because we have different numbers of neutrons. And we talked about, I think, hydrogen and oxygen as the examples. And here, notice that for oxygen, we have these different isotopes. And here I have stable beside each of these, right? So these are isotopes, they're stable. What do I mean by that? Well, they stay as oxygen. They don't get converted to anything else. And what do I mean by that? Well, there are isotopes that I would say are hot, all right? So, or radioisotopes. These are unstable. And these are elements or versions or isotopes of elements that will decay and become something different, all right? So they are unstable. And there's a desire, and I'm using bunny ear quotes again with my fingers, which you can't see, this desire, not that elements have desires, but they want to become more stable. And as they do so, they decay these radioisotopes into something else. And I'm going to explain how that works, right? But these more stable isotopes of carbon, for example, so carbon-14, we use for carbon dating in, say, paleontology. This doesn't stay as carbon, it becomes an isotope. Well, doesn't become an isotope, it becomes nitrogen. So nitrogen is much more stable. So it will be converted to that, right? But then you'll be thinking, well, I thought the amount of matter in the universe must be constant, so you're not going to make something new, and you're not. And I'm going to explain how this works, all right? So these radioisotopes, what they are producing is nuclear radiation, which is different from electromagnetic radiation or light, okay? So this nuclear radiation we often say is ionizing because it can be damaging, right? Depending on the type, it can penetrate our skin and cause the removal of electrons from molecules to form ions, which would be more reactive in our cells. And some of those could be free radicals, all right? And we already talked about those and how they can be damaging because they're going to try and scavenge an electron from something else, all right? And this type of radiation, ionizing radiation, can damage our most active tissues. All right, and they're more susceptible to that. So our white blood cells, for example, in bone marrow, okay? And I don't really talk too much about that because that's biology, but suffice to say, our white blood cells are the ones that we use to fight infections, and they're more active, right? So that could then lead to a cancer, for example. Ionizing radiation can also damage DNA, causing mutations. And again, this is more biology, but I'll mention a little bit later on in the course, very, very briefly. But DNA, we have our mature cells. If we damage that, we can cause a cancer, yes, but we can also damage the DNA in our germ cells. So if you're a female, your eggs, you're male, your sperm, and those kinds of DNA mutations can then be passed on to the next generation, which is even more disconcerting, okay? So, but ironically, if you know anything about cancer treatment, radiation can also be used to treat cancer. And again, why is that? Well, because cancer cells divide really rapidly, all right? And you can use it to treat cancer. And again, I'm going to speak really briefly about this later in the course because this is more of a biology thing, but it's applying chemistry. And if you want to, explore these ideas, you can definitely do it in a hot topics because it's still chemistry, even though it relates to biology, all right? Because everything's chemistry, as I said initially in this course, all right? So this ionizing radiation is what we call nuclear radiation, okay? But that's not to say that electromagnetic radiation isn't damaging. You know that some types of electromagnetic radiation are also damaging, right? Electromagnetic X-rays, all right? This is why you only have usually sort of a limit on how many X-rays you get done in a year because it can cause cancer. And the types of X-rays. So remember, X-rays, light is on a continuum of wavelengths. So the X-ray band, there's some of them are going to be more high energy than others, depending on where you are in that band, the X-ray band, right? Just like when we saw, the spectra given off by different elements, there's different degrees of reds, right? Different red wavelengths. So red is, a certain set of wavelengths in the electromagnetic spectrum. So the smaller the wavelength, the higher the energy, the more damaging, all right? Whereas radio waves are less energy, longer wavelengths. So those technically aren't as damaging. But I put this in my notes, and you can sort of see it. I put cell phones, ? This is on page 2 of my notes, and this is what this is here. Cell phone on. You can see there's energy here. Cell phone off, which you think of cell phones as radio waves, but so we say they're not damaging. But then this comes back to that old adage: sometimes too much of a good thing can be a bad thing. And this could change as research comes out. But in my notes, I say. High levels of radio waves over long periods could be damaging, right? So here the figure in my notes is 30 minutes of talking per day on your cell for 10 years might have a link to brain cancer, specifically glioblastoma. And that's the same kind of cancer that Senator John McCain passed away of, all right? But this is electromagnetic radiation, which is different than nuclear radiation. So I really want to make sure you understand that. So nuclear radiation being called ionizing radiation, all right? So hopefully that makes sense to you. I'm not expecting you to become nuclear physicists and understand all the nuances of it. But as a person living in society, I want you to appreciate that when you're talking about radiation, there's the electromagnetic radiation, which is from different wavelengths of light. And then there's radiation caused by what most people think of, and that's nuclear radiation. But all of this is included in that, All right, so now let's talk about these. There's a certain amount of chemistry that's happening here. And I said to you that you're having nuclear decay because these unstable isotopes want to become, or for the lack of a better way of expressing it, more stable. And in order to do that, they become other elements, okay? But there is a chemistry that's involved here because the amount of matter in the universe must remain constant. And that matter can also be considered is energy. And we're going to come to Einstein's equation eventually here, right? So, and we talked about some of these types of radiation already. Remember when we were talking about learning how we learned about the atom, and we're still learning about the atom, but how we learned about the atom, Marie Curie realized that there's certain elements that just give off energy without energy input. All right. And, you know, at that time, we already talked about alpha, beta, and gamma energy. All right. So these are these types of radiation that are given off, and they can be used to cause an effect. Remember, we used an alpha source to try and discover the neutron. So this thing had mass. All right. And here you can see, what is it? Well, it's actually helium. All right. We consider it a helium. You're giving off these alpha particles, which are helium. And you know, and they have mass. All right. And then we have beta. Well, what is that? Well, that energy is negative. We said it was negative. We said alpha was positive. We said beta was negative. Well, what is it? Well, it's an electron. It's not a valence electron or an electron that's going around the nucleus. It's an energy that is released from the nucleus in the form of an electron. Okay. And then we have gamma radiation, which we said wasn't positive or negative. It just had lots of energy, right? So here you have your penetrating power. So even while this thing had no mass, its penetrating power was extremely high. So you're losing a lot of energy. Here, beta was moderate and alpha was very low. Okay, so the penetration here is little, but it has mass, so much mass that we could use it to identify the neutron. Okay, now, and you can see some types of nuclear types of reactions that are going on here. So you could combine a lithium-6 with a deuterium-2, and you're going to give off 2 alpha particles, which, as you know, has mass, and that can then be used to doing something else. Okay, just so that you can imagine this. All right. So here we have, and what we're going to play with here is the atomic number, or the mass of the proton, or the number of protons, and the mass number, which is the number of nucleons, or the number of protons and neutrons mixed together. So that's the nucleon, all right? And that's how you can identify these different types of radiation, all right? So let's look at this. So the first one is an alpha decay, all right? Now, if you're going to lose an alpha particle, which I said is essentially a helium, and you're losing that from, in this case, your radon. And what you're going to make here is going to depend on what you're starting with, okay? And not every unstable isotope or radioisotope gives off the same kind of energy. It's not, you can't say that every type of isotope is going to give off an alpha. It doesn't. It depends on the element you're starting with, or the radioisotope that you're starting with, okay? So here you have radon-222. And it gives off helium, which is an alpha particle, right? So if you're going to lose, and you look at here, you're losing 2 protons and essentially 2 neutrons, right? Because that's helium. What's going to happen here is that your numbers are going to change. So your mass number is now going to drop by 4, and your atomic number is going to drop by 2. So remember, in your periodic table, you're arranging these with an increasing atomic number. So what you now have something different than you started with. So you have helium and polonium, all right? So you've made something new in the process, even though the amount of matter is constant, all right? So this is how you can recognize an alpha decay, okay? So now we're here on page 4 of my notes. So alpha, right? What you're doing is that you're giving off a helium, Now, the next one is beta, right? And as you know, that's negative, like a negative energy or an electron, okay? So something is happening here as in response, okay? So what's happening is that one of your neutrons is going to be converted to a proton, all right? And it's going to stay in the nucleus. As you give off this electron, and this electron is energy that's being given off by the nucleus. It's not an electron that's in the orbitals here, okay? And this sounds really weird, but this is very particular to radioisotopes that give off beta energy. Okay, so here you have a beta decay, and the example here is hydrogen. It's giving off this beta particle, all right? And what's happening here is that one of your protons in your nucleus, all right, is going to be converted to a one of your protons is going to be converted. One of your neutrons is going to be converted. I don't know what I just said. So here, notice that your mass number is the same, but your atomic number has gone up by 1. So one of your neutrons has been converted to a proton. All right. So whatever I just said, I don't know. I'm not going to restart this video for that. So one of your neutrons has been converted to a proton. Okay, so here you can see in my notes, page 4, beta, one of your neutrons is converted to a proton, but it stays in the nucleus, so your mass, your atomic mass, stays the same. And out comes this negative charge, all right? So, so out comes this electron. And this is very particular for elements or radioactive isotopes that undergo beta decay. All right, so not every type of radioisotope undergoes the same kind of decay, all right? But in this case, this hydrogen can undergo a beta decay and it can make a helium, okay? And in so doing, it's going to give off this beta particle, all right? And that's keeping the amount of matter in the universe the same, all right? So it's, it's very weird, all right? So this is how you can recognize a beta decay, because one of your protons you're going to look like you're going to get more protons because one of your neutrons is going to be converted to a proton, okay? Now, gamma, if you remember, it doesn't have charge, all right? But it has high energy. So what you're going to see here is it's going to look like there isn't any change to your element. That's what it's going to look like. But really, what has happened is that your nucleus has become less energetic because it has released this high energy gamma radiation, all right? So a gamma decay isn't as obvious as an alpha or a beta decay, all right? But you can detect it with a counter. Like if you had a radioactive counter, a gamma counter, you would sense, or it would sense this emission of this gamma ray, all right? So it's giving off energy, all right? But you're still, in this example here, you still have carbon 12, all right? And out comes this high energy gamma ray, all right? So this is how you're gonna recognize these, right? So with your alpha decay, you're gonna give off a helium, right? Let's look at this. You're gonna give off a helium. So your mass is going to go down by 4, and your atomic number is going to go down by 2. Beta decay, all right, one of your neutrons in your nucleus is going to become a proton, all right? It's going to balance out the fact that you've lost some, essentially an electron from your nucleus, which sounds weird because there's no electrons in your nucleus, but the energy is considered an electron, right? So it's the energy equivalent to an electron, even though there's no electrons in your nucleus. But in an unstable isotope or in a radioisotope, it will give off this beta particle. And how the nucleus is going to respond is that one of your neutrons is going to become a proton. So you're going to increase your number of protons. So this is how you're going to make helium instead. So you're going to go from hydrogen to helium because you've increased your number of protons, all right? Then for gamma, you're not going to change your atomic mass or number, but you're giving off a high amount of energy, right? So this is very penetrating. So remember I said back here, extremely high penetrating power. So you're giving off definitely some energy, and you're able to detect that with a counter, all right? Now, there's two other forms of nuclear equations that are really important to society because we use them in different ways. So one is positron emission and one is electron capture. Now, what are these? All right, so you can see if you're having a positron emission from fluorine, for example, you are making something different, right? So you can go from fluorine to oxygen, all right? So you can see that your atomic mass is staying the same, but your atomic number has gone down by 1, okay? So this is different from what we saw over here with beta, where we went up by 1. Here we're going to go down by 1, all right? So positron emission, a positron, now this is weird. So this is a particle that's equal in mass to an electron, but has the opposite charge. So it's given this electron with a plus on it, okay? So this is a positively charged particle that's coming off. It's equal in mass. It's not a proton, okay? And I know that that can be confusing because it looks like we've lost a proton, all right? But we've lost a positron. The mass that you've lost here is not equivalent. So what's happening in actuality, all right, when we're talking about a positron emission, is that one of your protons is becoming a neutron, okay? So you're not giving off a proton. I know it's confusing because this is positron. You're giving off a particle that's equal in mass but opposite in charge to an electron. And one of your protons is now balancing this out by becoming a neutron, all right? So it sounds really, really bizarre, okay? So a positron is a particle equal in mass to an electron but opposite charge, okay? And it looks like we've lost protons, but we're keeping our mass, okay? Our mass has remained the same, okay? So it's equal in mass, but opposite in charge to an electron. So it's very often written as beta with a positive on it, okay? And the change is 1 less proton, but 1 more neutron. Okay, so very, very weird, but you're not releasing a proton, you're releasing a positron. So I don't want you to get confused with this. The other one is electron capture, all right? So here, what's happening is it looks very much like a positron emission, but you're not giving off you're not giving off a positron, you're not giving off this energy. What's happening in this case is that one of the electrons from the inner shell is being absorbed by the nucleus, which is really bizarre, all right? So in order for this to balance out, you're losing a proton, but gaining a neutron, all right? So the difference here between a positron emission and an electron capture is that with electron capture, you're not releasing a positron, okay? But it looks like in terms of what's happening to the element, it looks very similar, okay? So one is electron capture and one is positron emission, okay? And in my notes, I have a bunch of practice things, and in the homework, you're also gonna practice this. But what I want to achieve here is just a baseline understanding of these nuclear reactions. And I want you to be able to recognize them for the exam, all right? So there's gonna be an example, and I want you to know, be able to determine, is it alpha, beta, gamma, positron emission, or electron capture, all right? So let's look at our summary chart here. So alpha decay, right? You're gonna decrease your nucleon number by 4, and you're going to decrease your atomic number by 2, all right? So this one should be pretty apparent when you see it. So if both of them go down, you know you got alpha decay, all right? And you can also predict what you're going to get, and that's what you're going to do with homework. Beta decay, there's going to be no change here to your nucleon, but you're going to increase your atomic number by 1, and you've lost an electron, all right? And again, that's not an electron from your valence shell or from your outer orbitals. It's energy that's released from your nucleus, and it's equivalent to an electron way of thinking, right? So gamma radiation, there's not going to be any change, but you're losing an incredible amount of energy that's very penetrating, all right? A positron emission, there's no change to the nucleon, but you're going to decrease your atomic number by 1. But remember, you're releasing a positron. And remember, that's equal in mass, but opposite in charge from an electron, which is why it's often indicated with this beta with a positive charge on it. Your beta, it's understood as an electron, okay? And then electron capture, you're absorbing an electron, all right? So, but again, there's not going to be any change in the nucleon number. You're going to decrease by 1 here, all right, in your atomic number, but you're not releasing a positron, all right? So here you've got, so that's the important difference here, okay? So hopefully you can recognize these. And I know that this is wild chemistry, and I'm not even going to pretend to be an expert on it, but it's important to be aware of these things, okay? Now, half-life. So very often, one of the ways we encounter these radioisotopes is half-life, and we use that to date things. So the carbon dating is probably what you've heard of the most, okay? So carbon dating, and that's because of the half-life. So these radioisotopes decay on a fixed time. It's really bizarre, but it's like clockwork, right? So given a certain half-life, you're going to have half of what you started with remaining. So remember I said to you that these things are going to be converted into a different element, and you just saw that. So when we're dealing with carbon dating, so C14, its half-life is very standard, and you can use that decay as it becomes nitrogen to date how old something is. Okay, and the reason this is useful, and that comes out in the video that's shown here, so carbon dating, is because the amount of carbon is C14 is fairly standard. But it's really important because carbon-12, which is the common isotope, doesn't decay. That will remain the same. So if you're an organism and you're eating and you're taking in carbon, and that's going to be used to build you as an organism, your carbon-12 will remain the same, whereas your carbon-14 incorporation, because it's going to work just like any other carbon, is going to decay with time. And they can use the ratio of that, the degradation of the carbon-14 versus your carbon-12 to determine how long or how old that fossil is, for example. How old it is, because that clockwork of radioactive decay is well understood for carbon-14, all right? So we call this the half-life, all right? And it's a logarithmic thing, all right? You're never going to be completely devoid of it, but it will go down by half each half-life. So here's your how much of your initial do you have remaining? Well, it's going to go down by 1 divided by 2 to the n, where n is the number of half-lives. And this video here shows you how to do some of these calculations. And indeed, in your homework, you practice it. I'm not going to put it on the exam because this is a low math course. But in your homework, you can try it out, all right? And there's no penalty for trying. And I would like you to be familiar with it, okay? Yeah, I don't have any practice questions in my notes, all right? But I would like you to be familiar with it. And here in this video, you can sort of see how it's done, all right? Now, where do we use this? Well, carbon dating. You can use different isotopes to date different things, okay? So carbon dating, it has a half-life, you can see, of 5,730 years. So if you're dealing with things on that time scale, that carbon is really nice. But carbon dating might be way too long for looking at other things, right? So something that's 100 years old, you might want to use tritium dating. So tritium is hydrogen-3, all right? And it has a much shorter half-life that would be much more meaningful to date things that are about 100 years old. Now, uranium to lead decay is very complex. but it is very useful when you're dealing with things that are really old, right? So you're dealing about the chemistry of Earth, so rocks in the Earth's crust, all right? And I'm not even going to pretend to be able to do this kind of chemistry, all right? This is like nuclear chemistry, all right? Or nuclear physics, I prefer to refer to it. But I want you to see that this is quite complex. So you might see a quotation of someone using uranium decay to lead, and notice lead also has some isotopes. So they're talking about uranium to stable lead isotope, okay? And this can take a very long time. So you can talk about billions of years here, you know, and then thorium here is 27. There's different types of thorium, different isotopes. And look at the complex decay pattern that you're dealing with here, all right? And again, I'm not going to even pretend that I could wrap my head around this. I'm not that type of person. But if you're a nuclear physicist, this would be fun for you. But here you can sort of see in all of the different elements that are, and isotopes and radioisotopes of these different elements that are involved. Okay, just so that you can see this, and that's the only reason I'm putting this here, okay? But these different isotopes, radioisotopic dating, you can choose your isotope to date whatever it is that you're looking at, okay? So here you can see lead, for example, skeletal remains would be very handy. Hydrogen, aged wines and brandies, carbon, you know, charcoal, organic material, and so on, okay? Now, what are other ways that we use isotopes? So tracers are really handy because these, you know, they'll be emitting, you can get counts, and you can look for, say, leaks in pipes, frictional wear and tear. And I've not applied this, but apparently the uptake of phosphorus by plants. So because there's radioactive phosphorus and you can track its uptake. And incorporation into a plant, for example, right? So phosphorus is part of our DNA, for example. And you can see as a plant grows and it makes more cells, and it will incorporate radioactive phosphorus into its chemical structure. And you could trace that if you had a detector for the emission that comes off of phosphorus, all right? Then there's all kinds of diagnostics. So we use this for medical imaging. And I think I already used that terminology. So diagnostic imaging. So if you go into a hospital, there'll be an imaging center if it's a bigger hospital. Sometimes it says nuclear medicine. And that's what they're referring to. So you can see here the different types of isotopes that are used, and you can see the different types of medical imaging that's used. This one I like to highlight, making power for pacemakers, right? So you probably know that there's, you can use nuclear energy to power submarines and, you know, the space station, but you can also use that to power pacemakers, right? So you don't have to keep going in and putting a new battery. So this is really interesting. I find it fascinating, okay? And then of course, radiation therapy, right? I already mentioned this. You can use this to kill, it can cause cancer, but it can also kill cancerous cells. And this is why patients undergoing radiation therapy have these signs of radiation sickness, right? As well. And it will also affect your fast-growing cells, which is why, you know, people lose their hair. But that also comes to chemotherapy, because a lot of these chemotherapies also affect your more rapidly dividing cells. So it doesn't mean that they're undergoing radiation therapy, it could be chemo, but we'll talk about this again very briefly at the end of the course, all right? All right, now, penetrating power, all right? So I already mentioned this, gamma, you know, very penetrating. In order to stop it, you need lead. Whereas alpha particles, you can stop with aluminum. And alpha particles, you know, even though they have the greatest mass, you can stop them with paper, all right? So you can sort of see, you know, the level of penetration and corresponding amount of damage that can be caused by them, all right? yeah, and when I was using these, radioisotopes in the lab, I-125 is a gamma emitter, and that's the one. I never used it myself, but I knew people who were using it, and there was a real jerk in my lab who would bring out his I-125 and put it on the lab bench, and then people would I'm pretty merciless. I freaked out on this guy. And you should be using it behind lead, and we had a setup, but it's just inconvenient to do that, because you have to do your work behind this lead shielding, and he just didn't want to be inconvenienced, and anyways. Whereas what I would use, I used a beta emitter, so phosphorus, P32, and I would just do that behind plastic shielding. So I had like a plexiglass shield that I could use, which was nice because you could see through it. But I still needed the shielding, so I'd have to work around my arms going around it. So obviously my hands and stuff would be exposed, but it would protect my core using the shielding. And so on, right? So alpha emitters, that would be more like your tritium and that kind of thing, which was annoying because it's hard to get rid of, but it's not damaging per se in that it would penetrate your skin. Okay, so let's keep moving forward. So now we're going to get into Einstein. So E equals mc squared. You've all seen this. So energy equals mass times the speed of light squared. All right. And what does this mean? Well, this nucleus, so this energy, so this is the energy of the nucleus. So this is the energy mass equation. And, when you're making, not that we can yet, we're trying, but when you're trying to make elements, all right, when those protons and neutrons combine to form a nucleus, there's a certain amount of energy that's needed to do this. So there's a small amount of mass is converted to energy, okay? And this energy is referred to as the binding energy, and the energy that's needed to hold that nucleus together, all right? And Einstein sort of figured this out, and he figured out what that would be. And the more stable that nucleus, the greater the binding energy that it has, okay? And there's a whole branch of science where people were trying to make elements and use that energy and put that energy in to make new elements. And this is what we call nuclear fusion, all right? I'm going to talk about that in a sec. And nuclear fission is the energy that's released when you split the atom, all right? And this is what Einstein was working on. And this is really important because if you look at your history, he was working on this understanding of the atom before the Second World War. All right, and he was, working away, and he was in Germany, and he was working on this, and this was really important in terms of how history played itself out, in particular American history, which is why we're going to sort of diverge a little bit away from chemistry to talk a little bit about the consequences that happened here. Okay, so suffice to say, this energy is this energy of the nucleus. All right. So nuclear fission was something that scientists became aware of sort of by accident as they were trying to work on nuclear fusion, to try and make new elements by forcing protons and neutrons together, all right? And it's kind of weird because breaking things is always so much easier, ironically, all right? And if you look at my notes, I mean, you can really follow this in your textbook. But basically what was happening is that while these scientists were trying to do fusion, they inadvertently were causing fission. And so what they were trying to do is make heavier atoms by combining, two less heavy atoms. And inadvertently, what they ended up doing was breaking atoms. And Lise Meitner, she actually was able to determine that this is what they were actually doing. She determined that what they were doing was splitting apart the atom instead of forming them, so fusing them. And it was her nephew, Otto Frisch, who coined the term nuclear fission, okay? And this is what I'm showing you up here. So what was happening is that you would take a neutron and sort of try to add it to a nucleus. And what you were doing instead was causing a fission that would then cause the fission of other elements, all right? So this is what we call a chain reaction, all right? And out comes gamma rays, right? And more neutrons, which would then cause more reactions out here, all right, or out here. So it's like it's like like dominoes. One domino is going to hit, knock over the next one, and depending on your placement, that can knock over a whole bunch of other ones. And I think you've all seen, people trying to set up these fancy dominoes, chain reactions, and how that works. So try to imagine it this way. Okay, now these were all scientists that, ironically, German, and they were working and you might also realize that a lot of these scientists, not only German but also Jewish. So so the societal implication that's happening here, as well as the scientific, we're all coming to a head in a way. All right, so here's Einstein realizing, this energy, and then these other scientists trying to make heavier atoms, and Lise Meitner just realizing that what they're doing is they're actually breaking things down. And then the understanding that the energy being released here could then be used to power an incredibly powerful bomb. All right, and again, this is taking place in Germany, and as we know, Germany was we say in the United States on the other side, right, and causing this world war, and instigating this world war, and these scientists in Germany, and then on top of it, many of them being Jewish. And we all know that the Third Reich had a thing against Jewish people. So it would actually be very dangerous for these scientists, not only for their life, but also because they were Jewish, they, hijacking their science if Germany, or the Third Reich or the Nazis realized this, and then harnessing this power for them to have a bomb of this magnitude, all right? So there was all of this, and I sort of play it out here with, these scientists included Fermi, Segre, Hahn, Strassman, Meitner, and Frisch, all right? And Frisch was working with Bohr, and you've already heard of the Bohr model of the atom, all right? Who then learned of this discovery, all right? So, paradoxically, Bohr left for the United States for a conference. And at the same time, Fermi also left for the United States. So Fermi, I believe he was Italian, all right? But remember, Italy and Germany were allied during the Second World War. So, this is why it's important for you guys to learn some history as well, all right? So Fermi already left for the United States. Runs into Bohr in the United States at a scientific conference, and they're all talking about this because that's what scientists do. They're all in the same field, all right? And this brought about this whole idea of bringing out Einstein from Germany and Austria, and all of these German scientists to the United States because of this knowledge. And there was this, and we'll talk a bit about this in class, but one of the reasons they didn't want to bring Einstein at one point, because they didn't understand everything that was going on in Germany at the time, but also because he had tendencies that were more left. And at that time, anything remotely left would be considered communist, and there's that whole other aspect going on as well. So they were like, oh, well, what if he's a communist, and all of that stuff that was going on as well. But eventually, as you all know, Einstein ended up in the United States. And so the important thing that they were understanding here, and that's what the scientists were trying to express to the American government, was that the science here could be used to power an incredible bomb. And as you know what happened with this, but at that time we didn't know how this was all going to play out. So fission of one nucleus, all right, releases not just energy, but neutrons that then cause the fission of other nuclei. And that sets off this incredible chain reaction, all right? So here you can start off with this, and it all started quite innocently as trying to fuse heavier things lighter things together to make heavier atoms. And if you remember my conversation about the periodic table, those bigger, heavier elements are hard to keep together, but they have these predicted qualities, which would be very, very great for society if we could figure out either how to make them or how to make them more stable, right? So this all began very, very innocently, but thanks to Lise Meitner, and as you can see here, Leo Szilard, right? They acknowledged that this could be a very, very powerful and dangerous bomb, right? If one learned to use the science and was able to control this reaction, all right? So, the political side of it then, bringing all of these scientists out of Europe, wherever they were, so Germany or Italy or wherever it was, and bringing them to the United States as a critical mass of scientists, and then, starting the Manhattan Project. Now, remember, this was very, very innocent because it was starting off initially with this desire for nuclear fusion. Now, why was that so important? Well, I already said to you about having these heavier elements because they're so important for chemistry that we could be doing as a society, but also because it can produce energy, because a nuclear fusion, that's what goes on in the sun. Okay, and we're going to talk later on about how we're trying to do this in the lab and use it as a source of renewable energy, because we're going to talk about that, I think, chapter 15. I'll mention this. But this nuclear fusion is what takes place in the sun. So that's thermonuclear reactions. And they were trying to produce similar reactions like this on Earth, because that would also be game-changing in terms of having an energy source that we could use in society. Okay, so that's the other aspect of this. Okay, so now let's come back to the Manhattan Project, right? So here you've got President Roosevelt in 1939. Now that was the start of the Second World War. That wasn't the official entry of the United States into the Second World War, but that's when it started raging in Europe, okay? And I know this because my mother was born in 1939, but as you know, the United States didn't officially enter the war until Pearl Harbor, okay? But Roosevelt already launched this Manhattan Project in 1939, all right? So this was now, and you can see I quoted, our scientists were brought to or fled to the United States. Many of them fled because they were Jewish, all right? Or of Jewish descent. So, this critical mass of scientists now in the United States then contributed to the Manhattan Project. And there was a lot of politics involved with this, as I alluded to with Einstein, okay? So there were 4 parts to the Manhattan Project. And this incredible thing about this is that none of the people involved in one part knew about the other people. Right? These were all like this level of secrecy that was attained here was incredible. So there's 4 branches. One was to sustain a nuclear fission reaction, right? So controlled fission, right? The other one was to enrich uranium, because uranium was a good source for fission, right? And then to also make fissionable plutonium. Plutonium didn't exist yet. But remember what I said about the periodic table, you can sort of predict the properties of elements based upon their placement in the table. So they wanted to make a fissionable form of this other element, plutonium, because that would probably produce a different type of fission reaction. And then the other one, so for step 4, was to create the atomic bomb itself. All right, and I'm sure now ironically, there's a race to produce this bomb, and I actually don't know if Germans even knew about this. I really don't know, because I'm not a historian. But ironically, this bomb was created, and it was created in the United States, and the only atomic bomb that was ever used by any country, and was used twice, and both times by the United States. So it's kind of weird how all of this played out. But as you know, it was used to end the war, and there's a lot of different ideas and opinions on that, and that's not my job. My job here is just to give you the history of the chemistry and how this all played out. Okay, so here we have the thing, and my notes are quite detailed here. So here, and I put them in the slide as well, so that we could talk about it in class, right? So, sustain a nuclear fission reaction. And this was Fermi's group, and we already saw his name, right? And he was now based at the University of Chicago. And he had worked out that neutrons can be used to trigger the reaction. And we had to slow this down, to increase the likelihood of those electrons to strike the uranium nucleus. All right, how did he do that? He used graphite to do that. And I don't know the chemistry behind it, but you use graphite and get a critical mass of uranium-235 in order to do that. And that critical mass needed a high purity of uranium, all right? High purity of uranium, 94%, all right? So we go back here. So step 2, enrich uranium, all right? So the uranium enrichment process was taking place in Oak Ridge, Tennessee. And Oak Ridge, Tennessee was a town, essentially, that was created of scientists and people there for this own purpose. And even the people that were working on the enrichment of uranium didn't even know why they were doing it. All right, so this was crazy. But if we talk about, and the way they did this was to use centrifuges. So you might realize when we were working out the Iran nuclear deal, they're always talking about the centrifuges in Iran. And the reason that is because you need a centrifuge to enrich uranium to get it to the required grade in order to make a bomb, all right? So you can see uranium on its own is only about 0.27% pure. So fissionable uranium. But you need to get it to, all right, so here, let's read this out. So, uranium was converted to gaseous UF6, and I don't even know how that works, but they have to do that to create a separate fissionable uranium-235 from uranium-238, okay, which itself, 238, can't be used, all right? But eventually, what you're going to get is really, really pure uranium-235, all right? And you need it to be above 94% pure, all right? So that's the idea here, right? So uranium on its own is fissionable uranium-235 is 0.27%, where most uranium is uranium-238, 99.27, all right? So you can't use this one, but you can use this one, all right? But again, it's a very, very rare compared to the uranium-238. And not only do you need to extract it, but it has to be 94% pure for this sustained fission reaction to take place. Hopefully that makes sense, right? And there's this step of making UF6 in order to do that, all right? Okay. Now, how do we make this other one? Fissionable plutonium-235, all right? So this was done at the University of Chicago. So notice both of these are University of Chicago. Glenn Seaborg's group, all right? That if you start off with uranium-238, you can convert that then to uranium-239, Okay, so again, you're starting off with uranium-238, which is, now this is a new element, and this is also fissionable. But in order to get there, you go over neptunium, which is also a new element, all right? And this plutonium was produced at Hannaford, Washington, all right? So you can see that even this was taking place in two different places, or being done in two different places, all right? So you had to, they actually made two new elements in order to get to here, all right? So the plutonium-239 was new, but in order to get that, you had to make this one, neptunium, all right? So there you go. So that was the second step. And then the fourth step was to actually create the bomb. And this, of course, you might have, Los Alamos, that you probably have heard this, and you've probably heard of Oppenheimer. Okay, so he made two different bombs, he or his group, one based on the plutonium-239 and the other one on uranium-235. So Little Boy, which was the first bomb that was dropped in Hiroshima, was based on the uranium-235, which was purified here using this chemical reaction. And Fat Man, which was the more powerful bomb, which was the second one dropped, it was based on plutonium-239, and that's the one that was dropped on Nagasaki. Okay, so this one, this mushroom cloud here, is supposedly from Fat Man. All right, so that is the sordid history behind this. Okay, now as you know, it isn't just the destructive power of the bomb that is dangerous, all right, but it's what is left over afterwards as well. Okay, so there's all kinds of nuclear fallout that comes from that. So the fallout in two different ways. Fallout meaning, the consequences of that bomb, and also the fallout being, what's left over after these chain reactions keep going. So there's a number of other isotopes that produce really deleterious effects on the body. So not only do you have radiation sickness, but you have all of these cancers that are caused by these extremely powerful isotopes. So three of the main ones are strontium-90, which accumulates in bone, iodine-131, which concentrates in the thyroid gland. That's different than the radioactive iodine that I used in the lab, which was 125. And then cesium-137, which accumulates in bodily fluids. And this caused all kinds of suffering afterwards. So not only were, people destroyed and vaporized by the bombs themselves, but afterwards, the survivors suffered for decades from these cancers. And many scientists worked, diligently to try and create treaties and all kinds of things, with politicians to try and ensure that these are never used again, right? And Linus Pauling was one of them. And he was also, as a chemist, I know his name well, because he also got the Nobel Prize in chemistry. As I think in my notes, I think I wrote down, he was awarded the Nobel Peace Prize because of his work, to try and limit nuclear bombs. But he also got a nuclear prize in chemistry, not a nuclear prize, a Nobel Prize in chemistry because of his work on bonding and protein structure. So as a biochemist, I'm very familiar with his name, even though, it's been years since I studied him and I might have forgotten the details as to why he got the prize in chemistry, but I just know he did. All right, so here I put it in my notes to work on bonding and protein structure. All right, and we'll talk about protein structure later in the course. All right. Now, how does that relate to nuclear power plants? And why do we care if Iran is trying to make a nuclear power plant? Well, because we're worried that they're going to try and make a bomb. But I want you to understand something, right? So civilian nuclear power plants, it uses uranium-235, but it's way, way, way less enriched than you would have for a nuclear bomb, all right? So it's only 2.5 to 3.5% enriched versus the 94% that you need for even the bomb that was used, at the end of the Second World War, all right? But again, it's used to, so what happens in a nuclear power plant is that there is a nuclear chain reaction that's taking place here. But it's highly controlled, and again, it's not as powerful as what you would have in a bomb, all right? But the idea here is not to release the energy for destruction, but to release heat. And that heat is used to make steam, which turns turbines to make electricity. So it's not like nuclear bombs going on in a nuclear reactor for a power plant. That's not at all the case. But in the general public, people think that, but that's not what's happening, all right? So the danger from a nuclear power plant isn't that it's going to blow up and cause a mushroom cloud. It just doesn't have the capacity to do that because there isn't enough energy being released to do that. But there is the amount of energy being released to heat water, and that then used to make steam, to make electricity to turn by turning turbines, all right? And there's two different kinds of nuclear power reactors, but you know, the long and short of it is that's what's taking place there. So that smoke you see coming off of a nuclear power plant is just steam. It's not dangerous, okay? So, you know, when we talk about the nuclear age, we're not just talking about nuclear power. We're talking about all the things that we've talked about, right? We you know, talking about the synthesis of new elements, chemical analysis. We're talking about carbon dating, tracers and research, medical diagnostics, and all of these not crazy, but incredibly useful things that come out of nuclear chemistry, which is why this is called the nuclear age, right? Even your smoke detector, there's a nuclear reaction taking place in there, all right? So this is what we're talking about. So we're not just talking about bombs, all right? That's definitely not what we're talking about. And remember, the whole, you know, the danger of a nuclear chain reaction, like here, came about because people were trying to do this, right? And as well, make these heavier elements that can be used for many of these applications, all right? Now, let's go back to this idea of nuclear power, right? So is nuclear power green? Absolutely. It's absolutely green, right? Because there's no greenhouse gas produced here, right? And if you go up to the nuclear power plant, as I have done with previous semesters of this course, you know, this is a very green energy, right? They're not making any type of greenhouse gas here. Well, not that we consider, that we normally consider. Even water vapor can be a greenhouse gas, but it's not one that we usually consider as a greenhouse gas, right? And we'll talk more about those later. So this is a really clean form of power that we can use, right? But why are we scared of it? Well, there's a lot of reasons, and you can see here, you know, the world use of nuclear power here. So you can see green, light green building their first plants, and I don't know how up to date this is, but there's probably newer stats on this. Building plants, considering plants, stable, the United States here building new plants. Here you can see so certain countries, all plants have been decommissioned, and I do believe that Germany is also decommissioning plants. And then other places, there's no commercial reactors or nuclear free. Some places they've declared themselves nuclear free, right? Now, but what are we, like I just said, that this is very green, and you can make a lot of energy, and you can also store the energy, right? Which, you know, which is an issue with a lot of green ways of creating energies. It can't be like wind and solar can't store, but you can store energy from a nuclear power plant, all right? So anyways, but what are we worried about? Okay, so when we look at nuclear power, United States, and you can see in my notes, 20% of our electricity. In Europe, it's much higher. France, 80%, Spain, and others, 30. But what is the problem? All right, so the problem is the waste, and even that doesn't need to be a problem. Okay, so the nuclear waste. So just like nuclear fallout, the nuclear waste causes problems. all right? And there is this worry that some of that waste could be converted to weapons if it's gotten into the wrong hands. And then decommissioning the fuel rods can take 3 years or so, right? And could there be problems, malfunctions? These are, famous things. 3 Mile Island in the United States, Chernobyl in the Ukraine, and Fukushima, of course, in Japan after the tidal wave, right? But if you go to the nuclear power plant, one of the reasons the building of a nuclear power plant is so expensive is not the plant itself, but because of the safety features that need to be incorporated in the plant so that it's considered safe, all right? So that is a huge cost. And I'm not saying that that is a bad thing, all right? But I'm saying that that's why a nuclear power plant can be so expensive to build, because of the safety checks that need to be in place, because of these worries of what happens to the waste and what could happen if there's a decontainment of the nuclear reaction and the isotopes that could be released, all right? Not because it's going to blow up like a nuclear bomb. It's not going to do that, all right? Now, and this brings me to a big but, there is a way to take that nuclear waste and then, and I'm still talking about this, but let's go back to my last slide here. There is a way to take the nuclear waste and build new plants, right? So the waste can be concentrated and reprocessed to generate more energy. So this requires a different kind of nuclear power plant, okay? But the technology exists. We could do it. But right now in the United States, they aren't giving licenses to create these plants. So they could essentially take all of the waste that has been produced so far and then take that remaining waste, repurpose it, all right? And that would then reduce the amount of waste to fit into a building the size of a small house, all right? And the remaining waste could then still be processed to be converted into harmless isotopes that could be used for other things. And this is to me the shame here, because we're missing an opportunity. But right now, in the United States, we're not reprocessing and recycling that waste, which is too bad, because if we did, we could not even have to worry about storing it anymore. We could just take that and make more energy out of it. But for some reason, we're not doing it. I don't know if it's political will or societal fears or what it is, but I think a lot of it is because there is this lack of understanding in society about what could be done. All right, but right now there's just no taste for it, and the waste is still there. So in future it could be used this way, but it would be so nice if we could use it, because again, nuclear power is green. It doesn't make carbon-based gases that cause the warming of the planet. Anyway, so with that, I think that's it. So let me just make sure on my notes. So page 15, other issues: safety, security, and high power plant costs. Yeah, so I sort of talked about all those things, and hopefully that gives you a good flavor of nuclear power, as well as nuclear chemistry, because we're not really going to talk about it anymore. The rest of it is going to be chemistry based on the outer shell electrons, which we were already discussing, and we're going to move forward with that now for the rest of the course. So hopefully that was informative and that you've learned some stuff, and let me know if you have any ideas for hot topics and anything else, all right?